God morgen alle sammen. Hjertelig velkommen til UiB AI-seminar om kvanteteknologi. Dagens seminar skal foregå på engelsk, så jeg slår like så godt bare over til engelsk med en gang. Welcome to number 13 of the UiB AI seminar series, and first one this year. And actually, this seminar is a bit outside of the normal schedule because, as you can see from the title, it's not really about AI, it's about quantum computing. And the reason we put this on the series is that there is a lot of talking about quantum computing and quantum technology these days. And we thought, well, first of all, what do we have at UiB? And then maybe more people than those who know about these things would like to know what this is actually about. So then we called for this seminar, and the interest is actually more than expected. We had 90 physical participants, and I think everybody came because I see that all the chairs are taken, and we expect many to follow online. And there will also be a recording, so you can also watch it afterwards. So this quantum, my background is from computer science, so I know it as quantum computing, but it's so much more. There's quantum sensing, there's quantum technology in many other ways. But when I was a PhD student in the 1990s, then every big computer science conference, they had a track on quantum computing. So this was really big in the 90s. And then somehow the interest faded, maybe at least in some areas of computer science. I think the interest from physics remained, and they went on with a little bit other kind of quantum technology than computing and algorithms. But definitely the field has secretly maybe has grown, and nowadays everybody is talking about quantum technology. So it's a little bit like AI. It was big in the 90s, then it had a winter, and then now it's back. But in a sense, it's really, really different from AI, because whereas AI methods are within the computer models that we have today, the quantum computing and quantum technology is something completely different, and it requires completely different kind of computers that are based off a completely different kind of physics, if I may explain it in this way. So it's new. And from the level of, we have many students with us today, so that's wonderful. We have the rector and the director with us today, so we have everyone from the students to the director who want to know about quantum computing, so that's very good. I'm really happy that we will have on the scene today, we have some of our experts from our university, from Simula UiB, which is a company owned by UiB, and the research center Simula, who do cybersecurity kind of research. And then we have people from Department of Physics and Technology, and then we will also even have people from our own IT department who will tell about how are they preparing for what's coming when it comes to quantum technology. So I'm looking forward to learn more about this, and I will now give the word to Dag Stenvold, who is the coordinator of UiB AI, and he will guide us through the program today. Enjoy.
Yes, welcome to all of you, and also to those thousands of you who are following this on stream. I'm going to very shortly introduce the first speaker, Konrad Tywoniuk, who is assistant professor at the Department of Physics and Technology at the University of Burheim. And his title is Quantum Technology, Opportunities and Challenges for Science and Society. Konrad, please.
Good morning, everyone. And thank you so much for the invitation to be here today on this very nice occasion. It's nice to see, as Pinar said, this cross-section from students up to the higher levels of the university. So this is a really interesting topic, and I hope to give it some justice here today with my presentation. This is a citation from the Swedish Minister of Education from last year. I'll directly translate. No one was talking about research in quantum just 5-10 years ago, but by now it's an established field. For me as a physicist, this is quite a funny quote. Maybe, lack of some historical context here, but in fact there is a point to this. There is a point why we are here today at this moment. As Pinar mentioned, now there is an explosion in interest of this topic. Companies, web pages on the internet, everyone is talking about it. There is a reason why. And in fact, I want to discuss, mostly since I'm a physicist, what are the quantum effects? What are these effects that make those devices, those algorithms different from the ordinary ones? I want to give you a few examples of how this technology is being used already. And the examples are from our own university. And then I would like to discuss, as my title indicates, some opportunities and some challenges that we face. So let me give a brief overview of quantum physics and quantum mechanics. Well, in fact, it's a more than 100-year-old topic. It's a field of research which has existed since the 1900s. Where Planck postulates for the first time the existence of a quantized unit of light that we see around here. It looks like it's uniform. It's coming all the time. But he had the postulate that no, there are quanta of lights, and those are called photons. Einstein followed up with several new ideas, but the main point where we can say that quantum mechanics was established was in 1925, where Heisenberg and his colleagues managed to invent a new type of theory that describes hydrogen levels, so basically the levels of the atom hydrogen. And this new funny rules led to the funny uncertainty relations coined by Heisenberg, where we basically cannot really determine the location of a particle, to put it very simply. The particle is rather smeared out over a certain distance, over uncertainty. There is an uncertainty related to the position of the particle. It's not located in space, which is very funny. So quantum mechanics is full of these kind of funny and counterintuitive facts. And this was, of course, more formalized or put in another context in Schrödinger's equation, where actually Schrödinger interpreted this as a wave function. So a particle, a specific object, doesn't have a concrete location. It's rather smeared out, and it's described by a wave function. I don't want to exaggerate here, but this kind of technology, this kind of knowledge gives rise to all modern science, especially in physics and related sciences and technology that we have today. The fact that we can look at a screen, the fact that we can use a laser, this is all based on quantum physics. This laser is a quantum phenomenon. The fact that all of these photons in this laser are quantized and come out with exactly wavelength that we want, a green, that gives us the color green, this is a quantum effect. This wouldn't exist if nature wasn't this way. Semiconductors, etc. The same thing in science, nuclear physics, the fact that we know that the nucleus is created up of different particles, they combine together. Even if we look deeper, there are other interesting subatomic particles that are studied at facilities such as CERN. This is all based on quantum physics, the quantum nature of reality. So quantum physics is really a paradigm shift of how we understand nature. And that's why this year has been promoted by the UN, actually, to be the International Year of Quantum Science and Technology, to acknowledge this kind of groundbreaking nature of this field, and it's exactly 100 years after Heisenberg's contributions and the other ones. So but why are we here today? Again, quantum physics has been around for 100 years, but why are we here today? Well, it's really in the last 5 years, that these kind of effects, quantum effects, not on such a microscopic detail, can be controlled technologically. So we can manipulate and control technologically these effects on really, really unprecedented scales by now. And this is because, in parallel to the research in quantum physics, there's also, of course, huge contributions in technology. So now we can really talk about quantum technology. That's why this term has now emerged, right? Where we can actually put this physics into applications, into the way we want it to be, not the way just to understand how nature works, but to kind of govern it. So quantum technologies are broadly defined into three other subfields. One is quantum computing, which is a new computing paradigm following the laws of quantum mechanics. There's quantum sensing, which refers to sensors that are also based on the laws of quantum mechanics, and they can be much more sensitive than existing sensors. And there's quantum communication, the way that we can secure information across long distances. But I will not talk much about that. I think the next speaker will be much more involved in that. So in short, quantum physics or quantum mechanics gives us new ways of doing computations and to perform measurements. So I think that's kind of the take-home message. Those are the two new areas where we can really take advantage of. So what is quantum computing? And to understand that, maybe we can look at the basic unit of information. So the basic unit in classical computers or normal computers, the one we used to, are bits, right? Everything, all the colors, all the numbers, all the different images in a computer, in the end, they are digitized. They are digitized into zeros and ones in this binary basis. So a bit is a way of storing information. It can be either 0 or 1, so either on and off. And combining bits, you can get these amazing things that we can do today. In a quantum bit, you have much more freedom. So a quantum bit is not anymore a 0 and 1 kind of state. It is a quantum state which interpolates between 0 and 1 in all possible ways. And we write it in terms of a wave function. So it's actually a wave function, meaning that it's not anymore either or, but it's and. It's both, let's say, dead or alive, both 0 and 1 at the same time. So how can we use this? Well, in fact, the only way to know exactly what this state is to perform a measurement. We have to send some light in or read out this thing, and then we will know exactly what the state is. I mean, the measurement determines. So you will get either a state 0 with some probability or a state 1 with another probability. So it's a probabilistic process. You can do this several times, and you'll get different results each time. So each time your bit is either 0 or 1 with different probabilities. So you can really control it. In a sense, this is some kind of an embodiment of some kind of parallel computing, in the sense that the qubit already stores a lot of more information than just 0 and 1. It stores both things at the same time. So that's the kind of a way to understand the simple thing. But then when we put more of these qubits together, we can start talking about building up algorithms, building up more complex systems. And this is manipulating single qubits by sending light in or shaking phonons or kind of manipulating these kind of things, and also to make them interact with each other and with their environment. This is how we can build up and control quantum algorithms. So we can manipulate these objects. These objects, this can represent a state in an atom. This can represent some kind of state in a semiconductor or just an imaginary qubit existing out there. It can even be a mechanical one. You can do this kind of manipulations to actually make this system perform an algorithm. And the interesting thing when you start manipulating this system is that you can create states. So not only is the one qubit more kind of complex than a single classical qubit, but also the correlated states that you create while manipulating them, they can also be very different than just a string of zeros and ones, which are completely independent. Here we can have states which are so-called entangled, or Bell states, in the sense that if I know that this atom over here or this qubit over here is 0, I immediately will know that the other one is also a 0. In a sense, I will know the state of the other one without actually performing a measurement on it. And that's because they're correlated in these specific entangled states. And that's That's this spooky action at the distance, which Einstein coined it. Basically, you can take these two qubits physically and separate them from each other. By measuring one of them, you will automatically know what the other one is. The funny thing is that you don't need to do this in a lab. There are many labs and a lot of research into this, but you can also go on cloud platforms, and you can get access to this kind of physics. You can start do kind of algorithms with these funny systems, and that's really a lot of companies involved in this development. So what can you use it for? You can use it for these 4 main areas, perhaps, is one way to organize the usefulness of it. You can do quantum simulations. There was a famous quote from Richard Feynman, a famous particle physicist from a few decades back. He said, well, if you want to simulate nature on the quantum scale, you want to simulate microscopic processes, well, you better have a quantum computer, because nature is quantum. So in order to capture all that weirdness, you should do it in a quantum computer. You can do quantum optimization, so you can, since the bits and the qubits have all of this intrinsic information, maybe it knows better where to find the optimal solution, because it contains all the solutions kind of in parallel at the same time. You just have to find the right one. You can do cryptography, and the next speaker will talk more about that, and you can also do machine learning with these kind of tools. And the interesting thing here, and the good news that I want to share with you, is that actually UiB, at our university, we have strong activity in all of these fields, without the quantum aspect. So we have strong groups and strong history in doing heavy simulations in many departments across many faculties. We have groups and activity in optimization, in strong activity in cryptography. We have machine learning used all over the place. So bringing the quantum aspect can actually enrich all of these fields. That I think is a positive message. Another way of doing this is, how we can use this physics is for sensing. Since we know laws of quantum mechanics, we know that these kind of states are very sensitive, and they transit among each other. The rules of quantum mechanics allow for that. Well, then you can use a sensor which will be sensitive to these transitions. So we can measure the change of energy of this transition or the rate of change. And by that, we can measure magnetic, electric fields that surround these qubits. So we can measure properties of the environment. We can measure pressure. Are these qubits squeezed together? We can measure acceleration, rotation. Are these qubits kind of flying around? And in the end, we can actually measure gravity and time. So in the principle, we can have atomic clocks, right? We can measure the passage of time and quantify that by this transition. That's our fundamental unit of time. It's the transition between two qubits. And this is really groundbreaking, I would say, at this point of view. Because if we know how to control these things, this can reach unprecedented levels of precision. We can measure positions in time and space and measure gravity to very high levels, and especially magnetic fields. That's probably the most interesting thing. So this is and this field, which I just spent one slide on here, this is probably the field that is most promising for industry applications and also for scientific applications in other fields than physics, for instance, biology, medicine, etc. So let me come exactly to two examples of how we can use this physics. So on one side, and I took the two examples from our department, and actually the one on the left is something I've been involved in. It's, first of all, computing toward optimization. You can find the best solution to complex networks. You can have complex networks like social networks, or you can have complex networks like, for instance, energy grids, which have producers of energy, consumers of energy, storage, and all of this thing is living its own life on the go. And this system is extremely sensitive to some shortages, right? If you suddenly get a burst of a huge amount of electricity being pumped in, it will break some transformer somewhere, or vice versa. If you suddenly have a lack of electricity, it's not only that your light will go off, it can ruin your whole controlling system. So this is something that has to be controlled in a very minute way. And one way to, and it's a complex system, right? It's all the way from our plugs on the wall into the huge power plants of hydroelectricity or wind power. So we really need, this is a huge field, ongoing field, but we gave a small contribution, and we tried to use quantum technology, quantum methods, to solve a basic problem, which is look for clusters in there. What kind of basic units can we group our network in to make it more efficient, so that we can somehow limit the loss of energy when we, for instance, have to talk at long distances in the network. Another very interesting application also from our department is more on in terms of quantum biotechnology and medicine. So this is quantum sensing for early cancer detection. Turns out that if you have an infection in your blood, or for instance something cancerous, then in your blood you have a lot of microRNA, pieces of RNA, or don't ask me what that is, something related to DNA. But that thing has a negative charge, electrical charge, and you can actually associate it with other kind of particles so that to make magnetic noise. Magnetic noise is actually what this sensors at the bottom here. This is a diamond full of small quantum objects, and this diamond sensor is very sensitive to what's on top of it. And by measuring the magnetic noise up here, you can say, oh, there's a lot of microRNA in your blood, or no, there's very little. And in fact, these guys, my colleagues, Eustace and friends, they really managed to show that you can detect even small amounts of this microRNA. And this is very, very promising for future applications. So now over to opportunities and challenges. I think, first of all, I would like to mention the crucial role of education. I think here we have a quote from the consultancy company McKinsey. You know, quantum technologies, they require a wide range of expertise. It's not just to know about some specific narrow field. You have to know a lot of different things. And you need to also have specific capabilities. You need to know how to use these things to solve your problem, right? Especially for quantum sensing. It's domain specific. You need to take those general principles and apply them. So this is a huge opportunity for us as a knowledge provider, as a university. We can really play a role there to improve this. And of course, also dissemination to the general public. We have to speak frankly about what this is, inform, and as we do now, to talk about it and to learn more about it from each other. Of course, the main thing is that these technologies can give us new paradigms in the way we compute things, the way we measure things. It can lead to interesting results. Now I'm taking the positive note on this. In a second, I will have a cautious remark about this. And of course, I think what's also very interesting is that it's so inherently interdisciplinary. When we talk about applications, we need to understand the fundamentals. We need to understand the limitations on the tools we have, but also how to apply it in the most efficient way, in the best way, in order to do what we want. And that's really, really interesting and has a lot of implications. Of course, there's a lot of activity in this, a lot of research, a lot of money into it, and we have to be honest, Norway lags behind. So the train is going, and Norway went off at Geilo and went skiing, and the train left, okay? And it's a super fast train, so now jumping back onto this train is going to be tough. But we shouldn't take that as, just, okay, let someone else deal with this. We have to try. I think also there is this point of interdisciplinarity is also something, a challenge, because it's very difficult, and I have been struggling with this for the last year and a half, 2 years, to connect, fundamental research, our knowledge of from physicists, from IT, from other things, and from biology, and from other fields, also engineering, and connect them. It's not so easy to meet an engineer. Well, and maybe in the physics department there are a lot of engineers, but maybe not the ones that I want to talk to, or other, biologists and things like that. We need to create areas where we can meet and discuss. I think that's missing. And of course, the final word of caution, probably, this is important. There's a lot of hype about quantum computers will take over the world. They will solve all the problems that we have, global warming, everything will be solved. No, probably the next speaker will also have some comment about that. There is no quantum supremacy. There is no, not everything will be taken over. But just as AI, as Pinar was also saying, it's a nice analogy. AI has come in and contributed in the ways it could into many, many different things, have given us new ways of analyzing data, etc., visualizing, analyzing, understanding. The same thing, I think, will happen with these things. So I think we have a few things to take with us. We need to raise awareness. What is these things? We need to talk more about it. Now is the year, perhaps. We can mark it in a nice way, 2025. We need to boost research. We need to work harder. We need to try to find new applications. We need to work to understand these things. And we should talk more together, I think, to get interdisciplinary and to find areas where this can be used. So thanks for your attention, and I'm open for your questions.
Thanks, Konrad. It's super engaging and very pedagogical talk. As a social scientist, I understood at least half of it.
Good.
So anyone have questions? We have a few minutes, 5, 6, 7 minutes.
Hi, Sigrun Eliassen. I'm a biologist. I was wondering, when it comes to the computational part of it, and you were showing an example from an optimization problem, is it sort of the speed or the amount of dimension you can introduce to these problems that is the, yeah. I mean, the potential of quantum, or is it something else?
It's both, yeah. It's both the hopefully, that's the hope. So it's yet to be kind of proven and completely established, but the hope is that it can go faster and that it can tackle more complicated problems, so that it scales better with the size of the problem, so you can attack bigger and bigger problems. What we managed to show is that we got a bit better solution than other groups could do, and that's kind of where we are now. But these kind of problems are inherently hard, so it's actually impossible to know the right solution. So it's a bit of a open problem. So if we just try to find a better one and a better one and a better one on these benchmark sets, but hopefully it could be kind of used in real life for better and faster solutions.
My name is Endre Tvinnereim. I'm a professor of political science. I also do a little bit of machine learning in my research, even though I'm for social sciences. This is a really fascinating talk, and I'm very interested in your points about interdisciplinarity. Mm-hmm. I'm wondering, how do you think the University of Bergen could support interdisciplinarity more to get at least some of the outcomes that you identify? Thank you.
Yeah, thanks a lot for this question. I think we can create areas like this, basically, where we meet. I heard about similar events and similar programs where we encourage interdisciplinarity. We can meet and come with different ideas and challenge each other. And I think this is really fascinating. I've been working a bit with biology and biotechnology recently, and I don't know anything. I have to ask basic questions about what is a toxicology, what is a cell, But this is really fascinating because from this we learn. So I think, meeting points. I think that's what we need. One of the things we need.
Pinar, again, with a question. So I've seen pictures of quantum computers. There are some huge ones and there are some tiny ones that you can place on a table. But I cannot really find good enough information about what problems and to which scale can we actually solve today. So I'm really wondering, do you have an example of like a easy enough to explain problem which we can actually use an existing computer to solve today?
Yeah, very good question. So at the moment, the limitation is they're twofold, and I didn't go into these technicalities somehow. But first of all, that we don't have many qubits available. We don't know how to manipulate many at the same time. And the second thing is that when we start manipulating, the more qubits we have, the more noisy it gets. We start losing control. So somehow they're connected to each other. At the moment, the oldest company that has been doing this thing and are selling their computer for commercial purposes is D-Wave, which is a Canadian company originally, and it specializes in optimization problems. So at the moment it has 5,000 qubits, and they claim that they can solve basically optimization problems with 5,000, let's say, variables. Which would perhaps, you could think about that as an energy network with 5,000 kind of transformers or whatever in between. But that, of course, is not really the truth, because the problems are much, much smaller. Because you need to correct for the errors, you need to do things. So it's hard to give a concrete problem, unless I would be a salesperson for Google and I would say, our quantum computer can solve this problem, which is completely irrelevant to the rest of the world, but it's super fast by doing it. But it's an ongoing race. It's an ongoing race. So actually, in our paper, we beat D-Wave. We show that we got a better solution than the real quantum computer. But it's an ongoing race, and everyone tries to get a better result.
Last question, Eric.
Erik Sandqvist. I work mainly with the funding of research infrastructures. And from that question, I'm asking if you look at education, so how much of the funding should we spend from a research council perspective, for sending our best minds out to these labs who have come the furthest, and compared to just building up our own labs here in Norway?
Well, yeah, that's a very interesting and good question. I think it's a very smart thing to send our students out. And in fact, there are efforts for Norway to join bigger consortia. So collaborate with Denmark, collaborate with Sweden, where this kind of field probably is more advanced, and also collaborate with other countries, of course. And I think this is extremely important to have well-established connections, but also, as you mentioned, so that we kind of also can gain from this expertise, so it doesn't necessarily go away, although we should have a huge exchange of knowledge. So yeah, I think it's I don't have an clear answer to that, but I think it's a really important aspect. Yeah.
Okay, thank you very much for that session.
Thank you.
And our next speaker is Carlos Cid, who is professor and director of Simula UiB, and he's going to talk about quantum cybersecurity.
Okay, thank you. So I'm going to follow up from Konrad's presentation, which was very good. So some of the stuff that I have probably be repeat, but also going to give a little bit more context and answer some of the questions that you had. So Konrad mentioned about some code from with all the analysis that go just in classical theory, because the nature is in classical, damn it. And if you want to make simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look easy. So even back then, in 1981, so Richard Kvamme already could see that this was a very difficult problem. And this was a natural application for quantum computers to try to work on quantum simulations. But the idea of quantum computers can be thought as something that you can try to then use, and the specific properties of quantum mechanics, Konrad mentioned some, to perform some type of computation. So hopefully some different computation. And the key concepts here, some of them was mentioned already, is superposition, amplitude, and entanglement. So some repetition here. So we saw already the classical computers, they work on bits, and usually bits stand for binary digits, so it's 0 and 1. And the idea of having 0 and 1 is that they're far apart, and for maybe north and south, positive and negative, and actually even comes to the fact that this can be correct sometimes, even if it moves a little bit, because they're so far apart, it can be correct. But quantum computers, they work on qubits, and we've seen this picture already, and then now means that this state is not either 0, 1, I mean, it could be 0 or 1, but actually is into a superposition of those two elements. So if you know linear algebra, essentially say that is a linear combination between 0 and 1. And it only sets into a definite state when it's measured, as Konrad mentioned. So this is actually, a lot of time people say is 0 and 1 at the same time. So actually I use this, which is imperfect, and at the same time. If you think about this coin, you see what I mean. And now, these probabilities are described by what we call amplitudes, which essentially are the coefficients that you have there. And this gives you a way of calculating probabilities when you measure, as Konrad mentioned. But the interesting thing here is the amplitudes can be negative. Although probabilities are positive, the amplitudes themselves can be negative. In fact, they are complex numbers. And this allows you some very interesting type of computation combinations. Typically, probabilities when you add them. But now here, because amplitudes they can be negative, they can cancel each other. And finally, they can also be entangled, as I mentioned. So essentially, some kind of new forms of a correlation. So the power of quantum computers come from combining and taking advantage of those 3 elements, if you will, to perform some different type of computation. If you don't take advantage of this, then the quantum computer is not going to be very helpful because this could be done classically. So when you design and when you look at quantum algorithm, it has to take advantage of entanglement and also the amplitudes and so on and cancel. So sometimes I've seen people saying that a quantum computation is essentially a very large experiment of cancellation. So if you think about what they're trying to do is that you set your input into some kind of superposition entanglement, and then as you perform the computation, it keeps canceling, the wrong solution keeps canceling out, and the right solution keeps adding up, and then eventually you measure, and when you measure, hopefully you get the right solution, because the probability will be higher. So that's kind of the way. So in a sense, if you're doing some quantum computation, you have to do a sort of physical experiment, and in this case, when you measure, you get the right solution. And now, how can you do this? So this is actually a quote, which is from the blog from Scott Harrison, who is one of the experts in this area. And then he's saying, if you're taking nothing else from this blog, quantum computers won't solve a hard problem instantly by just trying all solutions in parallel. So if you want to take something from this talk, you can take this quote as well. So quantum computers do not try everything at the same time, but rather it kind of evolves by canceling and adding the amplitudes and the probabilities, so that at the end, when you measure, you get either the right solution or the high probability. So what you do here is, you don't try, you're not going to be running classical algorithms, but try to use their potential. That's where the power of quantum computers will come. And in this case, we rely on dedicated hardware, which are quantum computers. So this is a photo here. I think this is from Google. So there's a question on quantum. So quantum computers today, there's a lot of different technologies on the hardware part. So we saw the little sphere. So this is, of course, is a logical way of describing, but in the real world, you actually don't have a little sphere. And so you have a qubit, which is a particle in this case, with the 2 states, and then there are different ways of realizing that. Same way that there are different ways of realizing the 0 and 1 in your computer. And so this is actually superconducting. So this is actually, the chip itself is very down there, but this is all about keeping the temperature very close to 0. But you have other technologies. And so today, it's not clear which technology will succeed. Some of them are better to keep this state, so they're more stable, but then it's difficult to communicate. And some of them are easy to communicate, but then they don't have. So this is not my area. I just follow what is going on. And also, you need dedicated programs. You need software. You need algorithms. So, for example, there is an algorithm called Grover's, which that's the way it kind of sort of looks like. You start with, I think you start with lots of zeros there, and then you do some kind of operation, and then you keep repeating this many, many, many times, and eventually you measure. And then when you measure, so this is an algorithm for unstructured search. Okay, so let's go to quantum cybersecurity. So of course, when we talk about quantum cybersecurity, I mean, maybe I could talk about quantum cryptography or post-quantum cryptography, but then maybe this wouldn't attract as many people, so I use this quantum cybersecurity because everybody. But every time when you talk about quantum cybersecurity, the first thing that comes in mind is that you have some hackers with quantum computers in some nation states, and they're trying to break into your account or recover your password. And that's not really what is going to happen. So when we talk about quantum security, really, we're thinking about one particular algorithm. So we started with a paper. And so this paper from 1990s from Peter Shaw, it's called Polynomial Time Algorithm for Prime Factorization Discrete Logarithm on a Quantum Computer. So this looks a bit, but you're going to know why this is important. But this is an example of what I mentioned. So Peter Shaw, he came up with a different idea to solve a problem, a type of problem. Prime factorization is the simplest one for you to understand. So if you take two large prime numbers, and multiply them, then you have this very large number. Now the multiplication is the product of two primes. So the multiplications are very easy, you can do. But then to factor, if I give this very large number with hundreds of digits, and I say that there are two primes that will multiply roughly the same size, and I ask you to recover there, this is a very difficult problem to solve classically. You cannot just keep trying. There are some clever ways, but it's still extremely hard, so it's exponential. But Peter Shaw showed that actually with a quantum computer, you can do this in polynomial time, which means very efficiently, if you will. But he's not actually trying to factor this in the way that we do classically by actually using these properties that we described. So this is an example of an algorithm that takes advantage of these effects for a quantum computer. So it runs only in a quantum computer. And so here, I'm going to talk very briefly now how this fits into cybersecurity. So I need to kind of talk a little bit about cryptography and so on. So, so I'm a cryptographer, and so security relies to some extent a lot on cryptography. Cryptography is the idea that is the secret writing, but actually today modern cryptography is much more than just confidentiality, but it's also data integrity, origin authentication, and much, much more. So some applications, for example, you don't care so much about confidentiality, but you care about that the data has not been changed, and so on. And cryptography is used today and everywhere for communications, for data storage, but also to secure computation. The main building blocks of modern cryptography, and so this is, you don't have to detail, so I just give you some examples. So we call public key cryptography, which you do encryption, and then you can establish keys. You have symmetric encryption, so there's block ciphers, stream ciphers. You have hash functions, so hash functions are, for example, used in Bitcoin. You have mass authentication codes and digital signatures. So this is actually little primitives, little kind of building blocks of cryptography that cryptographers usually study. And then you combine them to do something useful. So you don't have to, cryptographers wouldn't know all, they wouldn't be expert in all these areas. And then some people are expert perhaps in combining them and doing what we call protocols to solve some problems and so on. But this is kind of the building blocks that you find in the cryptographic mechanisms that you use today. And symmetric key cryptography usually are based on some kind of iteration of complex Boolean operations. So for example, you might see some algorithms called AES, it's no, so this is a stream cipher that, for example, is used in your mobile phone, so there's AES. And then you have hash function, SHA-256 is used in Bitcoin, for example, and HMAC and so on. So this is kind of a nice little showing the very complex way that the AES works. And then you have what we call public key cryptography, and these are typically based on hard mathematical problems. So they are different, this symmetric key and public key cryptography, they are different types. This one is more about mixing bits, and this one is about usually based on some mathematical problem. And there are some reasons for that. What happened is that the symmetric key is usually much more efficient, but public keys is slower, but solves some problems for you. That allows you to establish a key to use symmetric key. And here we have some examples, for example, RSA, Diffie-Hellman, elliptic curve, digital signatures, and so on. So this is a kind of, in cryptography, you have those two, symmetric key and public key. Now, so imagine, this is, again, another detour, how this is used in the real world. So when you use your browser to access a server, for example, Google, it uses a protocol to protect the communication called TLS. Okay? So how this is what happens? So your browser connected to the server, and we'll do the following. The first, the client here is your browser. So you connect to Google server. And then they're going to use public key cryptography, the one that's based on mathematical problems, to establish a share secret. So this is all done just so that we have a secret that we can share, because we didn't have before. Now, we also use what are called digital signatures to authenticate the server to the client. So you like to know that you're speaking with Amazon or Google and so on. And then the two client server, essentially the browser and the server, they use this shared secret that they establish to generate keys, and these keys are used then to encrypt the message used symmetrically. So it's kind of, you don't encrypt your credit card with a public key cryptography, but rather use public cryptography to establish a key that then is used with something more efficient. So that's kind of roughly the way it works, your protocol. And then you have the size of the keys and so on. Okay, continue now. So it happens that public key cryptography, the most popular ones that I use every day, are based on mainly two problems: integer factorization and discrete logs. So if you remember Shor's paper, the title was Polynomial Time to solve exactly those two problems. And those problems are hard to solve using classic computers, but they can be efficiently solved by quantum computing. So the consequence of all that, so Shor's algorithm and the way we use cryptography today, is that if there is a very large quantum computer, if you would call adversaries, adversary here is an expression that we use in cryptography, but you can think that the adversary could be even the person that you're communicating with. If they have a very large quantum computers with Shor's algorithm implemented, they could break the public key that we use today. So that's actually what the effect of quantum computers to cryptography that we use today. So the first question is, how large? How large is this computer? So actually, there is a paper from a couple of years ago that says how to factor the RSA integers, so essentially the ones that are used in the public key algorithm RSA, in 8 hours using 20 million noisy qubits. So I think Konrad mentioned a little bit the D-wave that has 5,000. So in fact, the D-wave actually is a different type of quantum computer. They use an annealing quantum computer. So the ones that IBM have now, I think has about 1,000. But this looks quite, difficult. So how far away is that? Well, so this is from NSM. So they actually have here, they say some people think that the quantum machine of this that will be affecting RSA will be about, 2030, so in 5 years. So, well, it was in 7 years when it was published. I actually don't like by the way, so I don't like the expression quantum apocalypse, because I think sort of, maybe plays nice for the media, but actually it's not helpful for what we're discussing here. Now, let's look a little bit more like an international and a more recent update. So this is run every year, the Quantum Threat Timeline Report. And this kind of ask about, I think about 35 experts that work in this area, what they think the probabilities that you're going to have a quantum computer that can break RSA 2048 in 24 hours, in the next 5 years. So kind of say, so you can see that, and then they have to give the probability. So this is quite a difficult exercise. But you can see that as you move further, there's, more and more people think there will be a very high probability, at least 70%, for example, that you're going to have in 20 years, you're going to have such a computer. So this is another way of visualizing that the way people become more pessimistic or optimistic, depends how you see it, that a quantum computer, that we're going to have such a large quantum computer that will be able to break this particular problem. And then, of course, it can break different problems. Okay, so, well, I mean, we mentioned 20 million qubits in 5, 15, 30 years. So this looks like kind of an interesting exercise. So who cares? I mean, do we really have to worry about that? So this type of computers people call now cryptanalytically relevant quantum computers. So essentially quantum computers which are large enough to run Shor's algorithm and break the RSA. So that's kind of a translation. The point is that this type of problem is not a problem only for the future. And so if you remember the way I explained how today we use in communication. So you remember that you use the public cryptography to establish a shared key, and then your communication is encrypted with the shared key. Now, what you could do, you could record this communication today, that you cannot break it, and you just keep it, and then maybe in 30 years or 20 years or 15 years, you go, when you have a quantum computer, you can go and recover and break. So the idea is that this is called harvest now, decrypt later attack. And this is kind of enabled because memory data now storage is very cheap. So you can think about nation states just collecting communication today, and then just keeping. And then maybe in 20 years, they will go there and they can decrypt, So this is particularly relevant when you have data that has long-term value. For example, medical data and government and so on. So this actually has pushed people to start migrating and to different, changing this now. So it's not a problem for the future, but for now. So what people are doing is that they're designing new algorithms. So they're designing new cryptographic algorithms, which now hopefully, Shor's algorithm, but not even other algorithms that can break it, based in quantum computers can break it. So this is called post-quantum cryptography or quantum-resistant cryptography. And in addition, there's quite a lot of work on industry support for migration and then risk management. So I'm not going to talk about particularly the item 2. The next talk, I'm going to talk about what is going on. So what I'm going to talk about is this what we call quantum-resistant or post-quantum cryptography. So again, the name here is a little bit unfortunate. So when people think about post-quantum cryptography, think that is a cryptography that's going to be used in the world after even quantum, in the future, but that's not. So post-quantum cryptography is the cryptography when you assume that your adversary has a quantum computer. So you can say it's classic cryptography, it's cryptography that we're going to use, actually we are using already, but the assumption is that now the people who want to break that, they have a quantum computer, and then you have to be based on problems which quantum computers cannot solve. So this is not running in quantum. There is something called quantum cryptography, but this is it's just the idea that you're working on. You assume that somebody has a quantum computer, so you have to protect against this type of attack. And sometimes called quantum resistant and quantum safe cryptography. So here I'm going to try to go quickly because I don't have much time, but so there's been a lot of work in the cryptographic community to try to come up with this. So it started in 2016, so there's a competition from the US. And then this is a kind of a model that the NIST, which is standardization agency in the US, has preferred for the last maybe 20 years. Rather than just design an algorithm and enforce, they have open competition. So this is started in 2016, then in 2017 was the loads of submissions, and then this is essentially cryptographers who work in this area have been quite busy on either designing or analyzing these proposals. So it's good for researchers, for PhD students, and so on. So this is all over the world. And in 2020, they announced the finalists, and then in 2022, they announced the selected. So here I just have for completeness. So they have one algorithm that is used to establish key, which is called Crystal Kyber. And then you have digital signatures. You have 3, Dilithium, Falcon, and Sphinx. So, and this is the teams that are actually involved. So there's been quite a bit of work to get there. Also, in July 22, they announced 4 algorithms which are still be considered to standardization. So-called BIKE, Class McLeese. So Class McLeese, actually, I'm part of the submission team, so my name is there, number 4. And then you have HQC, and you have this one Psych. But if you can see the website here, and Psych says, Psych teams acknowledge that is insecure, should not be used. So they selected this on the 5th of July as to be considered further, but the team said there was. And the reason was that 25 days later, people published a paper showing that actually you could break this in 1 hour. Okay, so this is an algorithm that's supposed to be resistant against quantum computers, but actually could be broken in 1 hour. And the point is that this is still. I use this example because this area is still ongoing. So it's still people don't understand some of these algorithms yet, and so there's a lot of work on this. So the standards have been published. So the three that I mentioned 4 that have been selected, 3 of them have been. So this is actually new standards for post-quantum cryptography. So these are algorithms which are based on problems which are not broken by Shor's algorithm and possibly not by any quantum algorithm. And this is actually, a lot of going on. So if you see some of the news and people talk about, the new standards, and so this is like from the World Forum, Europe finance sector must come together and prepare. And now the last part, I have 5 minutes, is to talk a little bit about this, what is happening now that we have these standards. So the first thing is, okay, so are we done now? We have post-quantum cryptography, can we just go home? And in fact, no. So this is, I have a quote. So this is a blog from one of the developers of Chrome. So he works for Google. And he's saying that actually the standards are not very good for the internet because, in particular, the digital signature. So he said actually it's too large, and there are some devices that this might not work very well. And this is another blog saying, well, the cruel irony is that just encryption has finally become ubiquitous. Quantum computers threaten to tear it all down. The reason is because maybe the algorithms are not as good to implement, so you're going to have to select where to use cryptography. Today, cryptography you're using for even things that you don't care, but maybe this becomes a bit different. Because of that, the competition is still going on, so they're still looking for other algorithms, so there's people still trying, in this case, for digital signatures. And there's much more. There's, in this area, people are still studying to see whether they are really secure. They're coming up with different other primitives. So this is just digital signatures and key establishment. But there's other quantum cryptographic mechanisms and algorithms which we don't have versions, at least trusted post-quantum. So people are still working quite a bit in this area. And then migration. So migration is what has a lot of activity going on. So now the point is, like, is this all necessary? So even if, the quantum computers are far away, and even if actually they were today, my application doesn't really care. I'm just kind of exchanging some, irrelevant information. So this is, I quote here, this is from BSI, which is the German security agents, and they say, from the point of view of question if or when there will be quantum computers is no longer paramount. The first algorithm had been selected for standardization, and post-quantum cryptography will be used by default. Therefore, people should migrate. And that's actually the status now in industry. Doesn't really care whether quantum computers are going to take 20 or 30 years. The train is moving, and people have to migrate. So, for example, here, you have in the US, they give the United States must prioritize timely, equitable transition by 2035. So all the US government systems, they have to be post-quantum by 2035. Here, also from the White House, and they say here they estimate they're going to spend, the US government will spend about $7.1 billion in migrating. Europe is doing the same, also pushing for migration. Here, actually, this is interesting. So this is just now, so a couple of days ago. So when Joe Biden was one of his final executive orders, he said, actually, no, you should actually migrate not until 2035, but must be prioritized as soon as practicable. So actually, the language was quite strong, saying we don't have to wait. So they should implement all the post-quantum now. So this is the executive order. So actually, I went to. So this is quite. It was new for me. So this is. I knew that. So I went to check to get the details. So I went for this, and then actually, that's what I found. So actually. So hopefully Donald Trump there's no one of the executive orders that he has taken. But anyways, the point is that it's showing that the US government is concerned, is worried, and is being pushed. And in this area where the US goes, everybody goes. So now here, just 1 minute. So then there's one very last thing is that was Konrad mentioned on quantum cryptography itself. And so this is actually not quantum cryptography, this is what we call post-quantum. But you could also potentially, when you have post-quantum cryptography, is the fact that the adversary has a quantum computer. Well, now, if everybody has a quantum computer or quantum resources, then maybe you can do things different. So there are different technologies which I didn't discuss, called quantum key distribution, quantum multi-party computation, verifiable computation, so there's a lot of, so this is a new area that once you have quantum networks, and then you can start doing things differently. So this is also kind of fresh and very interesting. And that's it. Thank you. And we'll follow for the next speaker. Will discuss how this is done to address that.
Thank you, Carlos. On this peek into the post-quantum world, I'm glad we're still living in the pre-quantum world, mostly. We have time for 1 or 2 questions, short questions.
Thank you. This was really informative. Jill Walker-Retberg, Center for Digital Narrative. So I'm wondering about how can we use quantum computing to encode and encrypt and keep our own data set? I mean, I've read sci-fi about entangled particles and secure stuff. Is that going to happen by 2020?
So this is the last part of the talk that I have to rush, and I didn't talk too much about. But what we've spoken so far, 90% of my talk was about essentially using class computers, but just based on problems which are not tractable for quantum computers. But if you have quantum, if you're going to transmit quantum information, then you can do things differently. And this is an area that is quite open. So, for example, there are potentially a few things using entanglement and other properties that you can do things quite interesting. So I'm just kind of getting into this area. But for example, quantum key distribution is an example of that. So essentially, you distribute keys, but not using RSA, but using the properties of quantum mechanics. But you have lots of different other things. Verifiable quantum computation, for example. If you're going to use if you're going to do quantum computation, which is outsourced, you like sometimes to verify. Classically, we know how to do this. For quantum computation, it's still kind of open how to do. So this is a big area there. Hopefully, in the future, as quantum networks become more ubiquitous, then we know how to do this with security. So we're going to need security. And the security that we have today do not work in the quantum networks.
OK, thank you, Carlos. And we're off to the third part, the last, yes. The last 15 minutes by Tore Burheim, who is head of IT division at UiB, and Sebastian Kvamme Bech, head engineer at the same IT division. And they're going to talk about how the UiB prepares for possible post-quantum attacks against its ICT systems.
Thank you very much. You have heard about the technology, we have heard about the security issues, and how we should worry. So what does the guy whose job is to worry think about this? And we're going to talk a bit about how UiB and the IT division is approaching the post-quantum cryptology, post-quantum security. And who are we? I am Tore Burheim, head of IT, as said. I have with me Sebastian. He has a master from the Department of Informatics in quantum computing. And he is working at the IT division in the security group. So at least we have got the competence, and of course we got it from the University of Bergen. This one. Before I start to talk about quantum computing and computing security, I always start with this slide when I talk about information security, because this is so important for all the works that we do. That is that it is good information security is extremely important for the core values, for the operation, for being a university with academic freedom, with autonomy and system. And it's an important issue regarding to integrity, credibility, and of course also into the daily business of being a university. And if it's not operating, it is important. And least also, if we are not able to take care of this, we know that it will be harder and stronger political steering and governance against us. So information security is not something that the IT division do for fun. It is something that we try to do to protect the university and the core values. So yeah, what do we do? This is the situation. This is what we have to address. And we know that we use quite a bit of encryption and decryption at the university. And all the communication that we have is based on these. We use it, this is the basic situation. And we know that by 2030, what we have today, we have to change all that. That might, okay, 5 years, no big deal. We have lots of time. But the problem is that, okay, there are some systems, there are some infrastructure. We have something like 1,000 servers. We have something like 500 systems to take care of. We have something like 3,000–4,000 Wi-Fi spots. We have something like 124,000 sensors around on the university. And all these have to communicate. And most of this communication is to be secure, and it's based on cryptography. And everything is need to be secure on that. So yeah, how do we add this? And also, of course, we know that Carl talked about this harvest now, decrypt later. And that is something that, okay, what we store it and what we archive today, we also have to ensure that this is safe after 2030. And some of our security data, some of the sensitive data within the healthcare and health data, we have to store it after 2030. So what do we do? Of course, we can do this try to put it very, very far away and very far, almost impossible to access. That is one way to do it. But also, we have to build good algorithms. We have quite a bit of, and what do I do as the head of this? I do not know much about quantum computing. I have Sebastian, and he is in charge of our work on the quantum computing. So, Sebastian, how are we? What's our approach on this?
Yeah, we're trying. Quantum is a subject basically for most people, from sci-fi movies, stuff like that. So it's nice that this subject is raised on this forum as well, and we try to do the same. I was fortunate enough to write my master thesis with Heggernes at Simula UiB, a very bright man, and I wrote it in post-quantum TLS, which was really nice. I got to dive deep into this, and I hope to use that competence to elevate the IT department as well, and our colleagues for the occasion. The things we're going to do, we started off, you can see the clear check mark here. We already know that we have sensitive data in person data, our research, stuff like that. So we already know that. Do access control. And in regards to what Carlos said about harvest now, decrypt later, you need to have access to that data to actually steal it, to decrypt it later. So this is a way to head start that progress into the post-quantum era. Then we're going to look at our technology, our protocols. Do we use safe protocols? Do our technology provide us what we need to actually do the migration? And is it safe enough to use? And then we're going to map out what we need to implement, what guidelines will be provided by NSM, what kind of certificates do we need. We want to implement the hybrid certificates as soon as possible, as soon as it's available as well. And we need to look at our solutions. We have log time storage and other valuable systems that we need to safeguard past 2030 and into the future, which has sensitive information that will be still sensitive in 10, 20, 30 years as well. And we want to implement everything we can as soon as the technology and the infrastructure is available for us to actually do that. So we're ahead, we're looking at what can be implemented, what will work for us, and where do we need to put this data. Also, as everyone else, we have systems that perhaps cannot be transitioned, cannot be migrated, will not be secure. And then we will have a plan for that as well. That would be putting it offline, so it can't be accessed, delete it, remove it, find out that this is more important to remove than to keep them, or use them, put them into our new systems. And this is the system we want to do to actually be in the future be possible to migrate and safeguard the data we have long into the future and into the quantum era.
Yeah, there's not much to say about this. It's a job to do. It's something that we had to do. It's not hard. It's not difficult. And what I see is that in the industry, in the supply chain, is lots and lots of activities. So yeah, everyone is implementing these algorithms, and we also get this hybrid solution such that we have a continuity, and the old system and new system can work together. So at the moment, I'm not worrying. So thank you to all.
Thank you for that, and we have time for a couple of questions if someone wants to know more about this. I have just maybe one question. I mean, you work at the IT division, but is there anything we should worry about to work at the rest of the UiB?
No, this is very, very technology close, so it's nothing that you need to worry about. Maybe you get some new system and upgrades. It will be this is a project on upgrading systems for the next, I will say, 5 years. Yeah. But we try to do it as soon as possible.
Yeah, I'm not sure if it is to the IT director, but I was just wondering if UiB has any plans to buy a quantum supercomputer.
I'm not. I'm not the person to answer that kind of questions. That is a discussion regarding research priorities. Yeah, I do not know about any plans. I've not heard about that kind of plans. So yeah, but.
You say we're trying to prepare. Can we be quantum ready without having quantum technology ourselves?
Yes.
Or is it going to sort of come as a surprise to us?
Yeah, if you mean hardware, yeah, perfectly well without the hardware. We do not need a quantum computer, whatever, to do that. This is about algorithms, yeah. So it's software upgrades. And maybe some hardware, I'm not sure. Yeah, probably some other stuff. You need to upgrade some hardware, but mostly software.
We have two final questions, maybe of a little bit more general nature.
Yeah, I'm just wondering, since we're at the UiB AI seminar, and no one really mentioned AI in their talk, so can somebody tell us a little bit? And I know there was one of the AI applications for the AI centers went in was on quantum. Could somebody tell me how AI is helping? Is it in helping optimize algorithms, or how are you using the combination of AI and quantum, just on a general level?
I think it's other people that is better to answer that kind of question.
I could say because...
Yeah.
I could speak. This is like, get to the microphone. Sorry. Carlos?
I could say something because I was part of one of the proposals for the AI Center, which is combining quantum and AI. So there are two aspects. First, quantum computers are being proposed to work on some AI problems. For example, machine learning, I think, was mentioned before. I think quantum computers, they are kind of machines that they work well with fast computation, but not large data, because storing data, quantum data is difficult. So they're not going to solve all the kind of problems. But there's this proposal to use for machine learning mainly, and there's quite a bit on this area. I don't work in this area, but there's also a proposal of using AI for quantum. So essentially using AI to solve some of, for example, implementation, or when you have a problem that you know how to describe this as a quantum circuit. It's quite complicated how to implement this. And this is like a problem that you have in computer science. You can have a problem how to factor a large number, but then how to implement this in a, you have to think of a clever way. So there's proposal of using AI to help that, to what's called transpiling, given a particular problem, how to find an efficient way in which this can be implemented as a quantum circuit. And finally, in the area of cryptography, there's also been proposing whether AI could help to analyze some of these algorithms being proposed. So there was a paper last year of one of these standards that being one of the algorithms being standardized, and there was proposal from a group from Meta, from Facebook, in which using AI methods potentially solve that problem a little bit faster. They've been just shown for small problems, but this is also an application in the sense of quantum to some way.
And a final short question from this gentleman.
Oh yes, so about the budget, how much would a quantum computer cost?
I do not know. I know. Maybe other.
You could perhaps
Sebastian, you know?
You could perhaps ask Oslo Met. They purchased one with 2 qubits, I think. So it's a small one, but it's still there.
Okay, so in a way, I think most places would not buy a quantum computer. Yeah. So you can use, for example, IBM. You can also get access. So I think the type of technology, it makes sense to have access and then use, and so the main large players, IBM, Quantinuum, I'm not sure Google, but Amazon, so they actually give you access, and I think this will be the cleverest way. It's not cheap, but at least if you're doing experiments or teaching, that's I think the most cost-effective way of accessing quantum computers.
And since I'm at the AI seminar, I can say that we should spend the money on GPUs to do AI instead of buying a quantum.
Yeah, I agree partly, but if you think about this perspective of 30 years, this access to a quantum computer is also something of like a national infrastructure. So Norway has actively joined a consortium to upgrade the existing supercomputers through the network of Sigma 2. There is a consortium. There's being built a quantum supercomputer in Czech Republic, as far as I know, LumiQ, which will have which will be a quantum supercomputer that is kind of owned by Norway. But this is a multi-billion dollar endeavor. But this is that's why we need big consortia. But the smaller ones we can buy for hundreds of thousands of crowns.
One last question before lunch. I like it when we go over time like this.
Thank you. Natalie Reuter, I'm a professor in chemistry with some understanding of the key concepts of quantum mechanics. So it's a question maybe to all of the speakers. So this estimate of when the relevant quantum computers will be available, is that based on technological breakthroughs, in which case the estimates are fairly vague, or do we know which steps need to be taken to get those computers?
Can you? I'm not.
Who wants to answer?
I don't feel like I'm not pretty good on that, or maybe
Yeah, I can try to answer that question. So there are currently several technologies competing to build these systems of qubits, but it's not yet settled which technology, and it's not clear which technology will be the best to scale it up to 20 million qubits, let's say it like that. So currently, as also Carlos was saying, we're talking about hundreds or tens or hundreds or perhaps thousands of qubits, but it's not at all clear that you can scale it up to 10,000, to 100,000, and to millions. So there's no clear leader, I would say, in the field of when it comes to technology. Should be superconducting devices or trapped atoms or whatever. So there's still kind of hope that there could be appearing a competitor on the market which is much easier to scale up. But that's really the bottleneck now, is to scale it up to millions, which there's no clear path how to do that.
Thank you, and that finalists of this seminar. Thank you, Tore and Sebastian. Thank you, Konrad and Carlos, for great talks, for enlightening us. Thank you for you taking part and engaging in discussions. And now we have lunch, vegetarian lunch, just outside until 12 o'clock. The next UiB AI seminar on 7th of March. It's a special edition in the University Aula, whole day, with some top AI researchers from all over Norway talking. So check it out. It's a cooperation with NORA, the Norwegian organization for AI research. So welcome back in March. Thank you.